When we go past grade 10 trigonometry, things progress quite rapidly and in directions that you wouldn't necessarily expect them to move. To you right now, trigonometry is basically SOHCAHTOA, and I'm sure you're familiar with that phrase. It's right angle trigonometry, the fact that the sine of an angle in a right angle triangle, other than the 90-degree angle, the sine of one of the acute angles, one of the small angles, is always equal to the side opposite that divided by the hypotenuse. And cosine of an angle is equal to the adjacent side over the hypotenuse, and tangent of an angle is equal to the opposite side over the adjacent. And your conception of what trigonometry is has to do with solving for lengths of triangles. But we have to be able to extend our understanding of trigonometry beyond that. For example, even though you can't really think of a reason why you would do this, it's possible to take your calculator and, of course, make sure it's in degree mode. Mine is in radians. It's possible, now I have I have an idea why you'd want to do this, but you don't. It's possible to take the tangent of 195 degrees. It's possible, and you get a number. There's a tangent of 195 degrees. If I try to take, say, the cosine of 195 degrees, what's interesting is it has a meaning and it happens to be a negative number. So there's more to trigonometry than you're led to believe in grade 10. It's not just about triangles, and even when it is about triangles, it's not about right triangles all of the time. So what we are going to be doing in this unit is looking at what's called an angle in standard position, and you'll notice that the angles have a domain, a set of values from 0 degrees to 360 degrees. This square brackets means less than or equal to in this context. This means 0 degrees is less than or equal to the angle we're going to be learning about, which is less than or equal to 360 degrees. We're going to be focusing our attention on angles either equal to 0 degrees, equal to 360 degrees, or in between. And, this isn't about your calculator, but I'm just demonstrating by talking about your calculator because it's familiar to you. These buttons are familiar. What on earth does it mean to say the cosine of 0 degrees is 1? Well, it has a meaning. Why is the sine of 0, 0? It has a meaning. We'll learn that in the coming days. Why is the tangent of 0 degrees, why is the tangent of 0 degrees 0, but the tangent of 90 degrees is not defined? There are all kinds of things we're going to be learning here, and it's not confined to angles between 0 and 90 anymore. The sky's the limit. In Math 30-1, we're not even confined with these limits. You can have negative angles. The cosine of negative 56 has a meaning. You don't know what it is. You can have angles bigger than 360. You can have angles less than negative 360. The sky is the limit. But in this course, we're going to be focusing on that range of values from 0 to 360. We're going to be looking at using the primary trigonometric ratios for those angles, even though as soon as you get past 90 degrees, you can't really talk about a triangle directly. We can still talk about the 3 primary trig ratios. And then we're going to be doing something else called the sine law and the cosine law. And I don't even really want to talk too much about that because that's later on, but suffice it to say, the sine law is not sine of theta equals opposite over hypotenuse. It's something different. Okay? To begin with, we're going to be looking here at lesson 20.2.1, section 2.1 in your textbook, and I've broken this down into 2 lessons. Today's lesson covers a couple of very narrow ideas, a couple of things that are just you need to know to move on. It's almost always about terminology in this lesson, although there's going to be a little bit of numerical math. We're going to be identifying angles in what are called standard position. We need to know how to sketch an angle in standard position. And then there's this thing called a reference angle, which is different than an angle in standard position. I mean, they might be the same sometimes, but they might not be. And this angle in standard position is also known as a rotation angle. And this is a pretty important idea here. There's something called a rotation angle and there's something called a reference angle. And they have different meanings. As I said, sometimes the rotation angle happens to be equal to the reference angle. But most of the time it's not. They're different. So this is the first foray in this course to, well, I guess we did it in the last unit, really paying attention to words. Words are important in math sometimes. Just like in the last unit, arithmetic, geometric, that divided things into two different approaches. Here, reference is different than rotation. And what we need to be able to do at the end of this lesson is sketch these angles in standard position. And if you know the rotation angle, which is the angle in standard position, you should be able to calculate the reference angle. And if you know the reference angle with some other information, you should be able to sketch the rotation angle and calculate the rotation angle. So rotation angles and reference angles are different. Just to let you know, whenever I talk about a rotation angle, I will almost always just use theta. I don't put a subscript on it. I don't slap a label on it. Theta is a rotation angle. If I ever talk about a reference angle, then I will write theta reference. Well, theta ref. That's my way of doing it. And although, as I said, the lesson is very narrow in what we're learning, there's not a lot to it, there's some technical things or some details that we need to pay attention to. And that's the terminology. So to begin with, coordinate trigonometry, not triangle trigonometry, but coordinate trigonometry deals with angles that can be drawn or represented on the Cartesian coordinate system, the XY axes. Okay? But we have to draw them in a particular way. A rotation angle, theta, is formed when we take an initial arm and we rotate it to some final position. So forget about the diagram in your textbook. Just look up here. If this is the initial arm, a rotation angle can be found by rotating it to a different position. And however many degrees I rotate it through, that's the rotation angle. Except we all have to use the same method of drawing these, otherwise nobody is speaking the same language. It's like everybody in a particular country having to drive on the same side of the road, so you don't get accidents or you get fewer accidents. We all have to use the same terminology and rules here so we don't have mathematical accidents. So somebody doing math here and somebody doing math in Germany understand each other. Okay? That final location, which is called a terminal arm, actually maybe I'll back up. Terminal arm means final location. When your plane lands at the airport and it taxis to the terminal, that's where you end up. That's where you end up being. If the vertex is at the origin, so when I did this, my elbow is the vertex. It's the point that's not moving. If the vertex is at the origin and the initial arm lies along the positive x-axis, then that is called drawing it in standard position. So from now on, anytime I draw an angle in standard position, I always look at the initial arm being on the positive x-axis, and the terminal arm is where it rotates to. This is a little counterintuitive, this next bit of business, but you will get used to it. This is an example of a rotation angle, and can you see the arrow on the end of that red arc? You can see it, right? It's rotating in that direction. And if you look at the second or minute or hour hand of a clock moves in the opposite direction. So clocks move in clockwise directions. This is counterclockwise, and the thing that's not very intuitive is that counterclockwise is a positive rotation. Okay? So anytime you see a positive rotation angle, in standard position, the arm starts here and it rotates counterclockwise however many degrees to the terminal arm. Counterclockwise is positive. If we wanted to deal with negative angles, negative rotation angle would be starting here and moving in this direction. All right, as a warm-up, on the Cartesian coordinate grid, first of all, label the 4 quadrants. How many of you remember which quadrants are numbered which? 1, 2, 3, 4. Gustav, what are they? How can I do this?
Like the top right is 1.
Okay, so I'm going to start at the top right. I'm going to put a 1 here.
And then it goes counterclockwise.
Goes counterclockwise. 2, 3, and 4. Perfect. See, I don't know if your Math 10 teachers taught you why they're numbered that way. I suspect maybe they didn't. I don't know. That's fine. I don't typically do it when I teach Math 10 because there's no reason to. I just say later on you will learn this. But it goes from quadrant 1 in the top right, and then it goes counterclockwise in numerical order. By the way, you can number them with 1, 2, 3, 4, or Roman numerals. So now we kind of get an understanding why they're numbered that way, and it has to do with counterclockwise as a positive direction for a rotation angle. Rotation angles starting at 0 and going all the way to 360 sweep through quadrant 1, then they enter quadrant 2, then they enter quadrant 3, then they enter quadrant 4 in order. What else are we asked? Label the locations of each of the following angles in standard position. So we're not going to draw the terminal arms and the initial arms because this diagram is going to show lots of angles. But that gray angle I have there, pardon me, that gray line that I have there is an initial arm. If I were to take that initial arm and rotate it counterclockwise 0 degrees, it's done, right? It's there. What that means is where that arm points is 0 degrees. This is the location of 0 degrees on the coordinate grid. If I rotate it now 90 degrees, and that number 90 is positive, so I have to rotate it positive 90, it's going to end up here. Now you're not going to draw these lines. You will draw the terminal arm later on when we need to, but in this diagram we're not going to draw any of those arms. But we can just label up top here that this is 90 degrees. And it doesn't really take a lot of thought. I think you're all fine with this to realize that if we go back to the beginning and I rotate 180 degrees, I end up here. If I go back to the beginning and I rotate 270 degrees is 3 chunks of 90, it's there. And if I go back to the beginning and I rotate 360, then I'm back at the beginning, which means this is 180 degrees, this is 270 degrees, and 0 degrees could also be called 360 degrees. Listen, I don't want to get too bogged down in what you're going to learn in Math 30, but I'm going to write down a few other angles here. You can write them down if you like or not. This is more of a Math 30 idea. And believe me, it gets more complicated than what I'm going to show you in Math 30. There would be nothing wrong with me writing negative 90 degrees here. Okay? Please don't get ahead of me in your note package. There would be nothing wrong with me writing negative 90 there, because that means you start on the positive x-axis and you rotate 90 degrees clockwise. There would be nothing wrong with me writing negative 270 degrees here. I'm not going to do all of these. There would be nothing wrong with me writing (810 degrees there. Because if I go from 0, which is where my arm is, and I rotate once around, that's 360. If I rotate another time around, that's another 360. I'm back there at what I'm pretty sure is 720 degrees, plus another 90 would take me to the top, and 720 plus 90 is 810. There's an infinite number of ways you can land in these positions. Okay? The angles may be different numbers, but sometimes the position is the same. Now, the last thing we're asked to do is to write a mathematical description of the values that the angles can have in that quadrant. So in this quadrant, theta, I'll go back to brown, which is what you're writing down. Theta has to be less than 90 degrees, but more than 0 degrees. And you do need to write the degree symbol whenever you write a number that's an angle in degrees. If you don't put degrees, then it means radians, and we don't even learn about what radians are until next year. The reason why these are less than and not less than or equal to is because this point right here and this point right here are not in quadrant 1. They're not in quadrant 1. The point at the top, this one right here with the green center, that point at the top is between quadrant 1 and quadrant 2. It's not in quadrant 1. It's not in a quadrant. So when we talk about the descriptions here, we don't use equal to in the inequalities. There we go. In quadrant 2, what we can say is 90 degrees is less than theta, which is less than 180 degrees. And in quadrant 3, it's 180 degrees is less than theta, which is less than 270 degrees. And in this quadrant, we can say that 270 degrees is less than theta, which is less than 360 degrees. And really, to be fair and honest with you, one of the reasons we're going through this warm-up is to familiarize yourself with some terminology, but it's more about getting you to think about these quadrants and angles in the quadrants, to pull your mind away from triangles and to think about rotation angles. All right, now we have a definition. We already know what a reference angle is. A reference angle in standard position is shown by taking an initial arm and rotating it counterclockwise around the origin to some final terminal position. A reference angle is defined as the smallest angle between the terminal arm and the x-axis. And what I want to highlight for you is this. I'm going to go back. You don't need to go back. I'm just going back here to show you something. When we take a look at this diagram that's on page 1 of your handout, I made a big deal of saying, look at that red arc. Do you see there's an arrow on the end of it? A rotation angle has a direction. A reference angle has no direction. A rotation angle is how many degrees and in which direction? A reference angle is just an amount of degrees. And it's the smallest amount of degrees from the terminal arm to the x-axis. So to learn what that means, let's get to the examples. Sketch a rotation angle of 60 degrees. Now, I didn't hand out a ruler. If this were a written response thing, you would want to use a ruler. You can use a straight edge of your calculator or textbook, or just a steady hand if you like. But 60 degrees means we are going to take an initial arm, we're going to rotate it counterclockwise through 60 degrees, which will be about here. And you don't need to draw the initial arm. Don't draw the initial arm, but you do need to draw the terminal arm. If you have a protractor, you can actually measure it. It doesn't really matter. But I'm eyeballing that 60 degrees, and we will need to become more familiar with these common angles tomorrow. 60 degrees is 2/3 of 90. So if I visualize this as a cake, and this is how much cake is left, and I want to cut it into 3 equal pieces, it would probably look like that. and each piece would be 30 degrees of that corner of the cake. I'm avoiding the use of the word pi here because pi is related to this too in a different way, 3.1415, etc. So what do? We draw that and we label in theta equals 60 degrees. And again, when I talk about a rotation angle, I don't use a subscript or anything. The rotation angle is theta. It's 60 degrees. Put that away. Now, what is the reference angle? Look at the definition at the top of the screen. The reference angle is the smallest angle possible from the terminal arm to the x-axis. So, I can get, don't draw this, I can get from the terminal arm to the x-axis this way. I can get from the terminal arm to the x-axis this way. I can get from the terminal arm to the x-axis this way. But what's the shortest way to do it? Well, the shortest way to do it is to just look at this angle. And look at what I've drawn. There's no arrows on it. I'm just saying that that is the angle between the x-axis and the terminal arm. And what we would do is we would say that theta reference, I'll label it here. I don't know how you're going to cope with knowing which is which. I'm using colors here. They're both the same angle though, aren't they? Except that fundamentally there's a difference. The reference angle doesn't have a direction. I know you might think, ah, big deal. It's important. But the reference angle happens to be 60 degrees. And I want you to ponder something. If the rotation angle is in quadrant 1, will the reference angle always be the same number as the rotation angle? What if this were 70 degrees, which is in quadrant 1? Would the reference angle be 70? Yes, so in quadrant 1, the reference angle has the same number as the rotation angle. All right, let's try another one. Sketch 150 degrees. So we might want to use our calculator a little bit here to decide, like I know 150 degrees is more than 90 and less than 180, but where is it? Well, 150 is 30 degrees less than 180. So if I were to swing an initial arm with its vertex at the origin counterclockwise, 180 would take me to there, but I only want 150, so I have to back off 30 degrees. I tend to try to think of angles in their relation to the x-axis, not the y-axis. Some of you might say, well, from here to here is 90, I want to go to 150, which is 60 degrees more. And there's nothing wrong with that. In either case, you end up here. We can draw in, I will always try to use the same colors here to be consistent. The rotation angle is 150 degrees. I don't need a subscript because it's a rotation angle. And the reference angle is this angle. Because it's the smallest positive angle between the arm and the x-axis. Listen, in other words, and this isn't going to come through on the video, you take the terminal arm and you basically drop it down to the x-axis so many degrees for a reference angle, or you take the terminal arm and you pop it up to the x-axis. It's always measured up or down from the x-axis to the arm. And the reference angle here will be equal to 180 degrees minus 150 degrees, which is 30 degrees. I want to go back and just talk about number 1 for a second here. We concluded that in quadrant 1, the reference angle is equal to the rotation angle. And just because these are both in the same statement, I'm actually going to write rotation. If it's in quadrant 1, the reference angle and the rotation angle are the same number. Always. Is this always going to be true if the terminal arm lies in quadrant 2? Why not? What if it were 91 degrees? What if this were 91 degrees? I think with just a little bit of thought, you will see that 91 degrees, I'm not going to be able to draw 91 degrees, but 91 degrees is something like that. If this is 91 degrees for a rotation angle, go ahead and calculate the reference angle. How are you going to do it? Aren't you going to take 180 and subtract the 91 to see what you have left over? It's always going to work. Because think of it this way. Do you agree, I should move this over a bit, that these two angles are always going to add up to 180? Okay, then 180 minus the rotation angle has to give you the reference angle. So in quadrant 2, this is always the case. And I'm using colors here, but you don't have to use colors. The reference angle will always be 180 degrees minus the rotation angle in quadrant 2. Let's take a look at the next one. 3. Well, 3 is in quadrant 3. 225 degrees. I would like everybody to use your calculator and/or your brain and figure out where that is. I know it's going to be in quadrant 3. How should we draw it in quadrant 3? Of course. By the way, when you draw these terminal arms, you need an arrow on the end of the arm. Where should I draw it? How should I draw it? Jay? Right, because if we take, and can you explain how you knew it was exactly halfway between the two axes? Okay. So Jay figured out that since 180 degrees is here, I'm just going to put this number here temporarily, and we want 225 degrees. He said, well, it's 180 degrees to here. How many more degrees is it? So he's taken 225 minus 180, I think. And he's getting 45. And then something in his brain said, well, 45 degrees is half of 90, which means that this is going to be, I'm never any good at this. I think it should be more. You get the idea. I'll see how well I did. That's not bad. I could nudge this over and say it's perfect, but it's close enough. So what do we draw? We draw an arc that does this, and we say theta equals 225 degrees. And the reference angle is going to be the smallest angle between the terminal arm and the x-axis, so that's indicated by that. We've already figured out it's 225 degrees. Minus the 180, which gives you 45. So the reference angle has a value of 45 degrees. This is theta reference. In quadrant, I'm not going to worry about colors right now. In quadrant 3, is this always going to be the case? Well, sure, because this whole, I can make this more general for you if you like. I don't know where this lands just in a general sense, but if it lands there, what we're talking about is this being the rotation angle. Pardon me, I said I would always use the same color. This being the rotation angle, this being the reference angle. That whole red arc includes 180 degrees plus the reference angle. So if you take the whole red arc and you subtract the 180, then you're going to get the reference angle. So that will always work. And I think you see where this is going. What if it's 310? Well, 310 degrees is going to be approximately there, roughly. In my mind, what I said was 310, this is what happened in my head. 310 degrees is 50 degrees shy of 360. Which means I'm actually, I kind of lucked out here. I've actually determined that this is 50 degrees. I've actually determined the reference angle in figuring out where to draw it or how to draw it. I figured out that it's 50 degrees. So the rotation angle is this, 310 degrees, and this is the reference angle. The reference angle is 50 degrees. And the reference angle will always be in quadrant 4, 360 degrees minus the rotation angle. Again, I'm not using colors here. I'll use the colors on the diagram. This is really the lesson. Once you get past what the definitions are for a rotation angle and a reference angle, this is the lesson. So in examples 1 through 4, we were given rotation angles and asked to determine reference angles. Now we're going to work backwards. Okay. A rotation angle in standard position has a reference angle of 32 degrees. Taken on its own, everybody, this is not enough information for you to find the rotation angle. And the reason is it doesn't tell you which quadrant it's in. And if it's in quadrant 1 or 2 or 3 or 4, the answer is different. And that's why the question says, what are the 4 different possible rotation angles? Sketch each one. Well, let's sketch them first. 32 degrees is about like that. I don't know. I'm not going to get out a protractor and measure it, but it's approximately like that. And that would be in quadrant 1. If I had it in quadrant 2, and by the way, the visual locations of these 4 diagrams have nothing to do with the locations of the 4 quadrants, right? They're just 4 diagrams. If it were in quadrant 2, then I would draw a terminal arm 32 degrees above the x-axis on the left side. If it were in quadrant 3, I would go 32 degrees below the x-axis on the left. And if it were in quadrant 4, it would be 32 degrees below on the right. So each of these angles is 32 degrees. And I really don't want you to get an overinflated sense of confidence here. This is not what trigonometry is about. It's partly about this because this is the language moving forward. It's going to get more complicated. Okay? It's just a basic introduction. So what is the rotation angle? Well, let's draw in the rotation angle in each case. And what you draw to make sure that you are talking about a rotation angle is you draw an arrowhead on the end of the arc. If you're doing some kind of written work for me, like a quiz, like maybe tomorrow you come in and we have a quiz on this, put your phone away, please, then it would be expected on a quiz or a written assignment that you put arrowheads on the ends of those rotation angles. So I'm going to put theta equals, theta equals, theta equals. I usually just draw the thetas in quadrant 1 because that's where the thing starts. And take a minute and calculate what the 4 rotation angles would be for each of those 4 situations. And your success here hinges on, your understanding of where 180 degrees is and where 90 degrees is and where 270 is and where 360 is. If it's in quadrant 1, it's kind of a no-brainer. You can see the angles are the same. When I look at quadrant 2, the bottom left of this corner, in my mind, it's just obvious I got to take 180 minus the 32. Those 2 angles, the red one and the green reference angle, add up to 180. So I get 148. Is that right? Just to warn you, whenever I'm subtracting angles, and I don't know why, it only happens with angles, I'm very often off by 10 degrees. I don't know why. So if I do make that mistake, let me know. This one would be 180 degrees, and I didn't do a stellar job of drawing that red arc. That red arc looks like it's just tipping over the x-axis, and it shouldn't. It goes right to the x-axis. I need to take that 180 degrees. Oh, my mistake. Pardon me, it should be going to the terminal arm, right? I need to take that red angle to find it. I need to take 180 plus the 32, which by my count is 212. Thank you. When I look at this one, to me it's immediately obvious that I have to take 360 minus 32 and get 328. Perfect. That's it. That's it. That's all. I mean, tomorrow the pace will go up, but this lesson is also very, very simple because normally today would be the day that I hand back your exams, but we did that yesterday. Okay. So you don't have a really heavy workload for tomorrow to get through. Get these problems done and you're done for the day, and that's it. Yeah, I'll give you a few seconds to get settled in and get going, and then I'll come around and I'll give you a hand.